So, hello everyone, welcome to the Physics Undergrad Colloquium. Today we have Khush presenting geometric prequantization from fish to waves. So, thank you very much.
Hello, everyone. I'm Khush. I'm fourth year math and physics specialist. My talk's going to be on geometric prequantization. So already before the talk even began, I was asked a question about why it's geometric prequantization and not geometric quantization. So I think um, I'll talk about that a little bit. So geometric quantization is a procedure basically that starts with a geometric description of of classical mechanics that then builds a quantum theory out of that classical theory. However, it's not that straightforward because we run into a bunch of issues. And the first step towards quantization is getting a pre-quantum theory, which is what I will explain how to do today. Okay, so one thing I must preface this talk with is that this talk is going to be quite mathematical because the content of the topic is more mathematical than physical. It is rooted in physical theory, um, and the ideas were initially presented by Paul Dirac when he looked at the Schrödinger equation, realized that there is a quantization type procedure to take classical theories into quantum. With all of this out of the way, I also want to mention that all the content that I present will hopefully be at the level of physics 256 and above. So if you have that baseline, you should be okay. So here's just a brief rundown of what it is I want to talk about today. So we'll first start talking about what quantization is. We'll then give a very, very brief history of quantization. Um, and then I want to give an introduction to Hamiltonian mechanics because this is actually um, this is a central step that you need in order to describe classical mechanics in a more mathematically sound way. And then we'll pre-quantize classical mechanics, and we'll do some examples just to get a feel for what pre-quantization actually looks like, and whether we even get the theories we hope to. Okay, what is quantization? The idea with quantization is we start with a classical theory, and then we make it into a quantum theory. However, this is an ill-posed question because at the end of the day, physics, as we know it, starts at quantum mechanics and then builds up from there with classical mechanics being a limit. And so we'll set all of those like questions aside, and we'll start with classical mechanics and then work our way towards quantum mechanics, just using a bunch of observations that we've seen. And the way we're going to quantize basically is we're going to look at classical observables. This is something I'm not sure is really presented in undergrad physics courses. So we'll talk a bit about what observables in classical mechanics should be. And then we hope to take classical observables and make them into quantum observables, which, as we know, are Hermitian operators. Um, and the goal of quantization would then be to take a classical system, assign its observables to quantum observables, and assign its state space, if you will, a Hilbert space. And we'll see how to do that. Yeah, so why do we care? We care because classical mechanics is a lot easier than quantum mechanics. And as I mentioned before, this is an ill-posed question. Like the entire premise of this is ill-posed to begin with, because it's like trying to find the value of a function only knowing its limits at certain points. Right? That's not really something that there could be many different quantum theories that have the exact same classical limits, sorry, and they all be incompatible. We'll actually see a situation like this arise when we talk about one of the examples with pre-quantization. So let's now give a brief history of quantization. Um, it all started when Planck realized that to solve the ultraviolet catastrophe, you basically have to make sure that energy of photons are quantized rather than allowing them to be a continuous spectrum. This is actually the central idea of quantum mechanics. Um, I also read somewhere that Paul Dirac ended up hating, sorry, not Dirac, Planck ended up hating quantum mechanics and he spent the rest of his life trying to like fight quantum mechanics, even though he was, I would say, the first person to even put forward that idea. Um, the next important step um, for the theory of quantum mechanics, I would say, is Heisenberg. When he introduced matrix mechanics, he actually did this high of coke, which is quite interesting. Um, and he was also really alone because he had hay fever, so he went off to some island because the pollen was bothering him quite a bit. The next step was Schrödinger, where he derived like Schrodinger's like his equation of quantum mechanics through Hamilton-Jacobi theory, which for some reason is not presented in 354, which I think is we stopped right before Hamilton-Jacobi, which is upsetting. Um, and then Dirac proposes canonical quantization, which we will see later on. And finally, the main mathematicians that worked on the idea of geometric quantization. So as you can see, like quantization was always a procedure since quantum mechanics began. But it was not until 1970 that geometric quantization um, was introduced. And so we, like I said, we won't really get into the weeds of geometric quantization. Quite abstract, and building up the theory requires a lot more work than I can really present in this talk. Okay, with all of this out of the way, we're now going to talk about classical mechanics. And for that, we're going to start with one of the basic notions, which is configuration space. So what is configuration space? Basically, it is a space of all possible positions a particle could be in. For example, if you had a pendulum, it is obviously a circle. So the configuration space would be a circle. If you've taken any like geometry courses, you would also require that the configuration be a configuration space be smooth in some sense. Along with configuration space in classical mechanics, we also care about phase space. So as we know from Newton's equations, um, we a system is not only determined by its positions but also by its velocities. But in our formalism of classical mechanics, rather than looking at velocities, we'll look at momentum. And so the phase space is basically all possible positions and momenta a particle could be in. Um, Mathematically speaking, this would be a cotangent bundle of like the configuration space. And as an example, for a pendulum, this would look like a cylinder. It is not quite a cylinder, but it'll look like it. So with this out of the way, yeah? Yeah. So um, you can imagine like taking a slice of this and saying that this is where zero momentum is, right? Because that's not canonically defined, at least in this picture. So you could like take a slice of it and say that, okay, this is zero momentum. And then going up and down the cylinder at a constant position on the circle would be the momentum at this point. And usually we call this a fiber. Okay. Okay. So you could do all of classical mechanics if you'd like with Newton's equations. Um, but after some point, they seem rather unfamiliar because forces are not the natural object we'd like to be working with. As Emmy Noether pointed out, we would like to talk about conserved quantities, and conserved quantities are very nice, whatever. They allow us to integrate the system so that we can actually compute things. And so we're going to look at Hamilton's equations instead. Hamilton's equations basically, instead of a second order differential equation that involves a function of the positions and velocities, will be a system of first order differential equations that relate a function called the Hamiltonian with the evolution of position and momentum in phase space. Okay. Um, um, I won't go into too much depth about what these equations are, but these are Hamilton's equations of motion. Basically, you have some function h that is called the Hamiltonian. In classical mechanics, if your system is like if energy is conserved in your system, then the Hamiltonian is the total energy. But this is only a classical object. And then with that, the evolution of the position is given by the partial derivative with respect to the momentum, and the evolution of the momentum is given by negative the partial derivative of the Hamiltonian with respect to position. This can be derived by looking at Lagrangian mechanics and looking for a system of second order differential equations rather than a system of, sorry, for looking, you can, if you want to look for a system of first order differential equations instead of a second order differential equation. Okay? So, okay, now we can ask the question of what an observable is. Basically, an observable for us will be anything that you can measure along the trajectory of motion. So it could be literally any function you want. If you wanted to know what position you're at, that is an observable. If you wanted to figure out what momentum you have, that is an observable. The total energy, that's an observable, and so on. And if you do some chain rule, you can, you can rewrite your like the time derivative of the observable along the trajectory. Give You can rewrite it like this. Um, Here, I'm assuming that we're using Einstein's summation convention, which basically means that this index over here, this I index, as you can see, is repeated, and one is upstairs and the other is downstairs. And whenever you see repeated indices like this, we assume we sum over. And we're going to call this thing in that I'm like highlighting it right now. We're going to call this a bracket. This is actually where the fish part, my talk title, comes from, because this is called the Poisson bracket. So yeah, as you can see, we can now define a bracket structure on the space of functions on phase space, and it's just given by this simple looking equation. You don't need to write it like this, but I think it's kind of funny. And we will see this wedge operation showing up later, so I'll explain what that is when we get. Okay, so what is a Poisson bracket? A Poisson bracket basically takes in two smooth functions and returns you a new smooth function. This doesn't have to be like the phase space of a manifold. Sorry, this doesn't have to be a phase space of any dynamical system. This could be any manifold you wanted, and it has to satisfy, it has to satisfy like linearity, because linearity is always nice to work with. It also has to satisfy product rule and anti-symmetry, and you could also say that you wanted product rule in both entries, but anti-symmetry actually gives you product rule in both entries. So if you assume product rule in one of them, you get them in both of them just because of anti-symmetry. And finally, we require it satisfy Jacobi identity. So if you recall vector calculus, this formula should be very familiar to you, because this is, the cross product in R3 satisfies this. So in some sense, you can think of the cross product as a Poisson bracket. Is there anything else? Oh yeah, the reason we want Jacobi identity to hold is because if you massage this a little bit, you can see an observable is if two observables are conserved, its Poisson bracket will also be conserved, and that's what Jacobi identity guarantees. Okay. So let's now do an example just to tie everything back together. So let's study, I don't know, let's study a rigid body. Um, there are two ways to look at a rigid body. One is we can think of the center of mass moving and then everything moving around it, or we could just look at the we can go into a frame where the center of mass remains fixed, and all we have to do is look at all the movements around it. In this case, our configuration space is going to be SO3. SO3 is basically the space of all possible orientations your object could have. So the next thing we have to do is define a Hamiltonian. The Hamiltonian, if you is given by the moment of inertia. Um, Mathematically speaking, this is actually a choice of inner product on the tangent space of SO3, and that's what this that's what this is. This is just the tangent space of SO3. So if you think of SO3 embedded in some space, you look at a direction that's tangent to it. Um, if you're a little clever, you can actually show that this tangent space can be identified with R3 and the cross product. That's where we get this Poisson mapping. Because as I said, the cross product satisfies Jacobi identity and all the other things. So this is basically how we get this. With that out of the way, you can then look at the equations of motion given by this Hamiltonian, and these should be familiar if you've taken it. So, okay, we've seen that like our abstract theory does lead to the right equation of motion in terms of a top. You can check that it'll work for any other system as well because we have just generalized what we see usually. Okay, you could now move back to Euler angles, and Euler angles are a way um, to relate how much you've rotated in each direction. So you require 3 Euler angles to give you the exact configuration of an object. You can basically think of them as how much did you rotate in x, y, and z. And one thing to note is that rotations do not commute. So you have to be very careful about which order you give them in. We won't really worry about that too much because it's not that important, but it is important to check, uh, like check your conventions and stuff. You could now take the equations of motions that we derived and plot them on a sphere, and this is the type of motion you get. So you see like some perihelions, which is something that we see in classical. Now, with all of that out of the way, we can actually start looking at the things that allow us to quantize. Base space, geometrically speaking, is rather nice. Okay. You can define an orientation of sorts, in the sense that you can tell which direction is up, which direction is down. Moreover, the geometry is quite nice because it allows you to define something called a symplectic form. That's what this omega right here is. This symplectic form basically allows you to find like summed areas um, that are spanned by 2 vectors in your space. And so if you wanted, you could have, let's say, this is x, this is y. Is this, can I draw it? Okay. Um, what this wedge product would give you is the area of this parallelogram. Okay. That it's just fancy notation for saying I'm taking the area spanned by these two. And then in higher dimensions, instead of looking at the area of the 4-dimensional parallelepiped, I would just look at the areas of each face and add those up. So I'm looking at sort of like a higher dimensional surface area type object. We can also, one way to also define this would be by looking at something called the symplectic potential, which is given by this object right here. You can take its differential to get the symplectic form. One thing to note is that this object is not defined globally always. And so this leads to the idea of like coordinate transformations and local theories and gauge transformations. One good thing about finding the area, like having a function that gives you the area, is that you can now take vectors and you can ask, okay, can I describe this vector completely by just knowing all the areas with all other vectors? And the answer is yes. The answer is yes. You can check why that is. And basically, you take now a vector field that looks something like this, and its inversion will give you some differential. Its inversion will give you some differential, and this will now play a role. Will play a role soon. So if you take a Hamiltonian, any Hamiltonian, you can ask, okay, is there a vector field whose inversion gives me the differential of that Hamiltonian? And it does. And this vector field is rather nice because if I act by this vector field on any function, I end up with the Poisson. So what this tells me now is that Hamiltonian mechanics boils down to just flows of vector fields, right? So I can leave all my physics behind and just look at general Hamiltonian systems and ask, okay, what flow does this, like what vector field does this produce? What system of equations does this produce? What is the flow of this? And you can derive a lot more geometric information um, from just this. Okay. So as an example, I've stolen this from Wikipedia. Um, you can see here that you have some flow lines given by the Hamiltonian for a pendulum. And this now gives you some really nice information. One, it tells you that you have closed orbits. Okay? So if you're in this region or this region or this region, you have closed orbits. Another thing to note is that this is 2 pi periodic. So all you really have to focus on is from negative pi to pi. Everything else will. Another thing this tells you is that there are some orbits that don't close in on themselves. So, for example, if you're up here, all you're doing is you start up here, for example, and then you go like that, right? Orbits down here would be something like this. And so all we did was plot a vector field and join its flow lines, and we got all that information about the dynamics of the system. So this is why we want to look at Hamiltonian mechanics. We want to look at Hamiltonian mechanics from a geometric standpoint. If you now have a Poisson bracket of the position and momenta, you get 1 if they're the same and 0 otherwise. If you take the Poisson bracket of like two positions or two positions or two momenta, you get 0. And if you've taken any quantum mechanics, it's extremely familiar to what Heisenberg derived, right? This is basically saying that in some sense, the commutation relations in quantum mechanics should be exactly the same as the commutation relations in classical mechanics. And this is the crucial insight you need um, to think about geometric quantization or any quantization procedure to, um, like, yeah, to any quantization procedure. One final thing I want to mention about classical mechanics is Noether's theorem, which states that symmetries correspond to conservation laws, and conservation laws correspond to symmetries. So if, but okay, there's like a small caveat that your space is nice enough. If your space is not nice enough, you can check out Lee's um, differential geometry book, where he gives an example of where this fails. Um, and this is something that you should always keep in mind when you're doing physics, because conserved quantities are your friends. So you want to find as many of them as possible. Okay, so now what is quantization? trading ceremony. Yes. Very nice. So now, all that being said, what is left? Because it seems like, other than that one pesky little detail when we talk, all basically everything that we would like with quantization has been achieved. But it seems that pesky little issue is a little bit too big. It actually messes everything up, and we have to now restrict our hidden space. And once polarization is done, you pretty much move free. You basically do pre-quantization. Pick a polarization, and then you restrict. Basically, you restrict the quantization procedure. But there are still many open problems